Welcome everyone to the seventh talk in our Quantum Summer Series, hosted by the Harvard-Radcliffe Society of Physics students. My name is Minchol Park. I am an undergrad studying chemistry, physics, and mathematics at Harvard, and I'm one of the organizers of our Chilloquium Speaker Series. I'm here today with my co-moderator, Whitman Go, and we are very honored to have Professor Alicia Kollár from the Joint Quantum Institute to speak with us today. As always, if you have questions at any time, you can raise your hand in the Zoom participant sidebar and we will call on you. Or you can privately send a message to me and I will ask for you. We encourage you to raise your hands to ask questions yourselves in order to make this feel as conversational as we can. So we will generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they are speaking and also have their video on if you are willing and able. And Whitman, please.
Lastly, for those of us who are joining us here for the time today, please subscribe to our Chilloquium mailing list through the link that Minchol will post in the Zoom chat. We send out one weekly email about the upcoming Chilloquium talk, as well as a reminder on the day of the event. So if you want to stay up to date on what talks are coming up, fill up the quick 15-second form in the link provided in the chat. All right, so with that, let's get started. Professor Alicia Kollár is a fellow of the JQI and a professor of the University of Maryland. Professor Kollár's lab builds experimental implementations of circuit QED systems using superconducting circuits. Professor Kollár's research will focus on using novel coplanar waveguide lattice techniques and graph theory to design and realize microwave photonic crystals with unusual structures such as gap, flat bands, and spatial curvature. Professor Kollár, please.
All right, thank you guys for the very kind introduction. I'm excited to talk to you guys today. I just wanted to second what the organizers have said. This is a relatively small crew, and sort of the point of this event is to for you guys to get to know me and what I do. So you should absolutely feel free to stop me with questions, whether they're physics questions or sort of more general questions. So at the behest of the organizers, I have split my talk up into two parts. So first, I'll tell you a little bit about how I got where I am and the somewhat winding road that I took to wind up in this particular field. And then I'll try to tell you sort of the main idea of what I do, maybe just a little bit of information for me. So how many of you guys have had a quantum mechanics class? Just to help gauge the right level. All right, so feels like I'm looking at about half of you guys are quantum mechanics, maybe half of you guys haven't. All right, I'll try to, as much as I can, sort of explain things both ways so that to keep things as general as possible. All righty, so let's get started. Okay, and so let me just turn off the Zoom controls. There we go, so I can see what I'm doing a little better. Okay, so as I said, I'm going to start a little bit by telling you guys the kind of stuff that I worked on before I started at the University of Maryland, and show you the kind of path that somebody can take that I changed fields actually quite a few times. So you can do a very large number of things in a physics career. All right, so this is the beginning of my physics experience. I'd like you guys to take a second and see if you can read the sign. So this is this joke sign in Feynman that apparently using over the controls to the beam accelerator at Brookhaven National Lab. And so this was something my high school physics teacher actually had posted in the classroom. And so he he was a cranky old guy, but he had a really funny sense of humor. So he liked things like this. And I was also a big Far Side fan. And so that was really where I first got interested in physics, because my high school physics teacher was sort of snarky and sarcastic and liked the same strange Renaissance music I did. And he actually gave me a copy of the Feynman lectures with a stamp Bullwinkle for president on the inside cover. And so that made me think that these physics people, they're fun, right? They're weird nerds of variety. And I think in general, that's true. And so I have been both happy with the science and the work that I do and the people that I work with. Another one of our favorite cartoons. Anyway, so now let's get to my undergraduate career. So I was an undergrad at Princeton, and actually my first sort of research experience was a summer job with my mechanics professor. And so I picked the one person in the department that I knew, and I said, can I work for you? And so I wound up working on their experiment, and this particular group was doing things measuring the cosmic microwave background. And so in general, actually, all of their experiments were in the Atacama Desert in Chile. And so what I got to work on was a prototype telescope. And so the idea was that they were going to make a self-contained shipping container that had a telescope that could measure the polarization microwave background. And in the back half of the shipping container, there would be a control unit. And so this is a photograph of me inside the shipping container trying to get it ready to house the telescope. And so basically my job was to build a frame inside of the shipping container that would be strong enough to hold this 3,000-pound telescope. And so in the picture, you can see me, and I'm covered basically head to toe in machine oil because I was in the process of making and building this whole thing. And so this green frame was my creation. You know, I'd never bulk ordered from a supply company before. That was a first. You know, it arrived on a truck and had to paint the whole thing green to keep it from rusting. And I put the whole thing together. And I think all in all, it was about 1,000 pounds of steel. And so it was me hanging out with this is my forklift. It was for my own personal use that summer. And I actually used it to like lift up all of the beams so I could bolt everything together. And then I think another one of the funny stories from that particular summer is, so the way that I built this frame, I built sort of one wall first, sort of freestanding in the middle of the room, hanging off of the forklift, and then I had to move it over to the wall. But after I assembled it, it weighed about 400 pounds. And so what I discovered was that if I borrowed a sledgehammer from the machine shop and I just pounded on it, I could sort of get it to move over. So that was the kind of summer I had. It involved power tools, machine oil, sledgehammers, and my own forklift. And I thought, this is fun. And so I actually went back to that group again the next summer. And so I don't do cosmology anymore, but what I discovered was really fun was building your own apparatus, right? You set a goal, you figure out how to do it, you try it, it doesn't work, you take the whole thing apart and you fix it, and so the first time I put this frame together, it was a 1/2 inch too tall. So it didn't fit. So I had to take the columns out and take them to the machine shop and like cut 1 inch off and then put the whole thing back together again. And it was still a little bit too tall. And then I cut holes in the wall, actually. I was a little desperate. But so, that was my summer. And I realized I really liked building things. And I liked the sort of hardware debugging aspect of the whole thing. And I didn't really care whether it was a power drill or some super fancy piece of equipment. There I was building something with my own two hands. And that was a lot of the theme of my physics research, is that I liked to build things. It's a little bit less true about what I do now, but that's really where it started. So I discovered that I could build. And then the next thing that I decided to try was condensed matter physics. And so I did my senior thesis in condensed matter physics, and that was a generally unpleasant experience. It was a bad lab and a bad fit for me. And so when I went to graduate school, I did something else. So I tried to combine the theory of condensed matter physics, which I really liked, with the building aspect of the cosmology research that I had done in my summers as an undergrad. And so this is what my grad school stuff looked like. So this was a picture of one of the BEC experiments in the lab. And basically when I started, there was an empty room. Actually, when I started, there wasn't even an empty room. First, there was an empty room, and then we put stuff in it. And so again, it was a big building project. And so we had a vacuum chamber and lasers and magnetic field control and the lab stuffed animal hanging out in the corner. And so, you know, I had a really good time building that. But, you know, one consequence of being a builder on a new experiment was actually the first paper I ever published was in my 5th year of graduate school. So don't let anybody tell you you can't go to graduate school if you don't have a paper. They're just lying. And don't let anybody tell you that you're a loser if you don't have 2 papers of your own by your 3rd year of graduate school. They're also lying. You know, if you do a big long haul project, then that kind of stuff happens. And so what I did in graduate school sort of ended up setting the general theme for my research. And so what we were trying to do was make a new kind of system where there was, an atomic BEC in an optical cavity. And so the goal of this was to get a new sort of feedback between the atoms and the light. And so it would lead to a new kind of self-organization. And so I designed and built the whole thing. And as soon as I graduated, they started publishing really nice papers. But it was really fun to build. And at that point, basically, what I knew about myself was I liked physics, I liked physicists, and I liked building things. And I had sort of become an expert in interaction between atoms and multiple enhanced modes of the electromagnetic field. And so what I knew was the multi-mode cavity QED. This is the fancy words for it. And so then it was a little bit of an accident how I wound up doing a postdoc in a completely different field. So I applied to about 5 different groups to do a postdoc, some of them in sort of cold atoms. So that would have been the same kind of apparatus that's shown in this picture. And then 2 of the groups that I talked to were using artificial microwave atoms. So they were superconducting circuits groups. And as it turned out, none of the atomic physics groups had any openings. And both of the circuit QED people that I talked to had open jobs. And so a little bit accident, I wound up going actually right back to Princeton to work instead with artificial atoms. And so this became what my apparatus looked like. For those of you with an eagle eye, will actually see the good old forklift has made a reappearance. I went down to the physics building and I stole it back again. Nobody else wanted rusty action forklift, but I actually put it to use assembling some of the apparatus. And so, but I had basically changed over from using actual atom lasers to using qubits and microwaves. The physics of these systems is very similar. The Hamiltonian is essentially the same, but the actual hardware and measurement techniques are pretty different. So it was a bigger change than some people do for a postdoc, but the goal of a postdoc is actually really to learn new things. And so some people feel like they have to go do exactly what they did before because that's the only way they'll be an expert when they hit the ground running. But really a huge amount of the point of a postdoc is go somewhere new and do something different and shake some new ideas loose. Get some experience that you didn't have before. And in the end, I stuck with what I did as a postdoc because I had some very nice ideas for what I actually wanted to do. So that brings me to being a professor. This is what my lab looked like about fall 2019. An empty room, a bunch of holes in the wall, and a very large pile of trash. So I think the first time there was a graduate school visit day, and I was trying to encourage students to join my lab. I sat in my lab literally in the middle of a pile of trash because it had been used as like a communal lab space and everybody had taken their equipment and left their junk. And so I sat there in this sea of trash waiting for people to come and to try to convince them that this was a really cool lab to be in. It didn't work out so well with the sea of trash, but and now I have a few students, and actually this is what it looks like now that they've finished remodeling it. And instead of using a vacuum chamber, we use a dilution refrigerator. And everything is in the microwave, so signals go in and out of the fridge on coax lines. And this is sort of our setup. And so then the question is, what are we trying to do with this? What are my grand ideas? And the basic overarching theme is that if you work in microwave circuits, you actually have a huge amount of flexibility and control for the environment that the microwave photons live in. Basically, everything that was developed for room temperature microwave circuits, you can try to modify to do physics with it. And so you sit down with a computer drawing program and you can just make a new circuit, and in this new circuit, the physics that your photons will feel is going to be different. And so you have a huge amount of control and a huge amount of flexibility. You can really design for one thing or another much more easily than for light. Basically, light waves are too fast and the wavelengths are too small to have a lot of control, but in microwaves, you can really play lots of games. And this is what we are trying to exploit. And in particular, my specialty is to make basically artificial materials for microwave photons. So at a very, very high level, if you want to think about a material, then what this is you have a collection of atomic nuclei, and electrons can sit on one nucleus and move neighboring nucleus, and they can sort of hop along. And so if you want something that emulates or reproduces some of the physics of materials, all you need is this sort of periodic array of sites. And this is an idea that has been used in many different fields. For those of you that have any experience with ultra-cold atoms, you can have atoms hopping in an optical potential, and that's an artificial material. So what I specialize in is actually artificial materials for microwave photons. And if you do it with these kinds of circuits, then it's possible to make materials that are basically materials, or maybe a better way to say it is laws of physics that you can't actually access in the lab any other way. So you can make a little miniature world for the microwave photons that is different from anything else that you can access. And so this is the building block that we use. It's called the microwave coplanar waveguide resonator. This is a schematic of what it looks like. You guys are probably too young to have ever seen analog coax cables on a television or a sound system. But basically what this is there's this center pin right here, which you send signals down, and then the outside is ground plane. And so this is a waveguide that channels microwave photons. And if the center pin is continuous, then this is just a very nice cable that can transmit. But if you cut holes in the center pin, then you create an impedance mismatch that causes the microwaves to bounce back. And so you can make a standing wave cavity for microwave photons inside this broken waveguide. And this is one of the main workhorses of our field, not just for the more sort of synthetic physics that I do, but also for a lot of the superconducting quantum computer technology. This is one of the main types of resonator. In practice, it looks a little bit more like this. And so actually, when you look at it like this, you can see the similarity to a cable even more, right? So like if you have a cable and it's too long and it's just getting in the way, then what you would do is coil it up to sort of compactify the excess length. And so these are 2D, so they're sort of cut into a single superconducting film. So we can't coil, but we can do the meanders. And so that's what these zigzags are actually doing, is they're letting you take a relatively long structure and produce it in a smaller block. This is actually a very key property of these resonators, which we're going to exploit. And from the physics point of view, this is actually just a harmonic oscillator. It's a harmonic oscillator of the electromagnetic field, but if you close your eyes and don't think too hard about what X means and what P means, it's really just a harmonic oscillator like you learn about in freshman mechanics or in quantum mechanics. And so this is our sort of microwave harmonic oscillator that we use, and this is also our photon trap. And so these can have quality factors in the 100,000, maybe a million range. And so that sort of means that if you have light circulating in this cavity, then it tends to have about 100,000 oscillation cycles before it drains away. And so that tells you how well the light is actually confined in these things. And so, even though in free space, light just goes whizzing off, here it's sort of stuck dinging back and forth for many, many round trips. Okay, and so then other half of our tools is superconducting qubits. Let's see. So the main qubit that's used in my field now is the transmon qubit. I don't know how much you guys have heard about this guy. So there are sort of two ways. The main way that people think about qubits is sort of just any form of artificial magnet. So a quantum magnet, the smallest possible quantum magnet, has sort of two states. It can point up or it can point down. And so if you sort of take a step back and zoom out, then any quantum system where you have two states that you can control and not deal with any other states, you can think of this as an artificial little mini magnet and therefore as a qubit. And that's what the transmon is at a more microscopic level. What it is a nonlinear harmonic oscillator. Right. And so when you look at a harmonic oscillator, it's the Hamiltonian is x squared plus p squared. So you have a parabolic potential and you have momentum. When what the transmon is a circuit where instead of x squared, you have cosine x as the potential. So it's sort of a bit shallower than a standard parabolic potential. And so it gives you oscillator levels that are very similar to a harmonic oscillator, but not quite identical. And one of the big differences is that the spacing between the levels isn't uniform. And so that means that if you shine in a microwave tone that's resonant with this transition, it's not resonant with the next transition up. And so if you're a little bit careful not to drive too fast or hard, you can isolate these lowest two levels. And so basically almost anything that anybody does with superconducting circuits is some combination of combining microwave harmonic oscillators with an artificial mini magnet made from some nonlinear harmonic oscillator.
Professor, I have a question at this point. So
yes,
is this anharmonic oscillator is kind of defect in the system that is like no way to make it better to be harmonic, or is there the reason why they make this kind of anharmonic system?
It's very deliberately anharmonic. And so basically, one way to think about this is that the harmonic oscillator is the simplest possible thing that you can have. And its simplicity is both very nice and very limiting. And so, if you, let's say you want to make a synthetic system that has, let me put it this way, the oscillator is perfectly linear. There's no nonlinearity whatsoever. And so that means that everything is power independent. And one of the consequences of that is that there are no particle-particle interactions. And so from a physics point of view, that makes harmonic oscillators extremely boring. You solve the single particle problem and you're done. There's nothing else. Good, we can go home. We've solved everything. From the, say, quantum computation perspective, you end up with a similar result, that the harmonic oscillator isn't complicated enough to be able to sustain interesting computation. So you need something more complicated than that. And in fact, one of the things we wish for is something that is actually much more anharmonic than this. So the ideal qubit is a two-level system where there's exactly two quantum states involved, because then you don't have to worry about having an accident that leaves you in any of the higher levels. And so there's a sort of complicated history behind why the transmon is the best. It's the best because it's relatively immune to materials noise, but it's not actually the best in terms of being highly nonlinear. That's sort of its Achilles heel, is that it's only mildly nonlinear.
Oh, I see. Thank you so much.
Yes. And so basically the toolbox that we have is we have harmonic oscillators, which are very easy to work with and very flexible, but they have a sort of limited physical capability. Qubits are trickier to work with and a little more tetchy, but they can actually do a lot more physics. And so sort of the challenge in our field is to combine them in ways. All right, so I think maybe I will skip the dress state picture. This is a little bit the wrong level for this audience. It's sort of the basic idea here is that you can actually you can just literally draw one of these superconducting qubits inside your microwave resonator, and then you automatically get very strong coupling between this sort of artificial magnet and the microwave photons in the cavity. And you actually get much, much stronger coupling between this artificial atom and the microwave photons than you can ever get between a real atom and an optical photon. And so there's a lot of physics that people originally thought up for real atoms that works very badly, and it actually works much, much better here in the microwaves. And so the fundamental building blocks is really this strong light matter interaction, and it allows us to do two things. So one is we can control how the spins or the qubits interact with one another using the microwaves, or we can actually use the spins to give the photons an interact. These are two sides of the same coin. Basically, when you couple them to one another, they inherit properties for each side. And so my particular specialty is to take what is an artificial material for the microwave photon, and then to start combining these with the qubits. And so when you do that, basically you get a qubit-qubit interaction that is determined by the microwave structure that it's in. And so my specialty really was realizing that we could take a device like this one here. This was made in the Haut group at Princeton a while ago now, that we could take this kind of device and rearrange it and get to all new kinds of materials. And so, all right, so how does that work? And sort of why is it interesting? All right, so this is, from my point of view, this is a small piece of a solid. And so each one of these squiggly lines is a microwave coplanar waveguide resonator, like we saw a couple of slides ago. And they meet at these little black dots. And so what's happening in these junction regions is that the center pins of three of the cavities, they come together. And when they get close together, there's a little bit more capacitance. And so that allows a photon that's rattling around in one of these cavities to jump into another one. And so you can think of this as a network of lattice sites where microwave photon remains largely confined, and then it hops over to another one. And this is sort of the same way that an electron would move in a solid. It stays somewhat bound to a nucleus, and then it can move to another nucleus, et cetera, et cetera. And so this is how we think of this thing as an artificial microwave material or a microwave photonic crystal. For those of you for whom this Hamiltonian has any meaning, it really is described by a type binding model for microwave photons. And so the key that makes these systems interesting is that this coplanar waveguide resonator is a very, very different lattice site from conventional atoms. Okay, and so the first property that's really interesting is what I was hinting at earlier, that this thing is like a cable. And so you can change the shape without changing the properties. And so the way to understand this resonator is that light is just traveling along this waveguide. It hits the end and it bounces back. And so frequency depends just on the total length. And the coupling comes from these ends. And so what that sort of means is that you can independently change how strongly it's coupled to its neighbors from what its own resonant frequency is. With atoms that tend to have, let's say, a spherically symmetric orbital, the distance to the neighbor of the center of mass is really what sets the hopping rate. And you can't just make an atom larger or smaller. It's really stuck at a given size. But with these, you can, for example, make these three different shapes. And so to you and me, looking at this at optical wavelengths, these look like totally different resonators. But from the point of view of microwaves in the device, these look exactly the same. And so what this allows us to do is have microwaves move on chip way that's not compatible with the geometry of the lab. I think since I talked a lot about certain things, I'm going to skip to why this is cool. And so the idea that we had was, we have these resonators that can bend and change shape. And that means that in a certain specific way, the distance that microwave photons sort of travel in the device is different from the on-chip distance. So if I look at two things and I say, these are 2 millimeters apart, it doesn't mean that the microwave photon travels 2 millimeters yet between. We can add these extra detours and decouples the distance that the photons feel from the constraints in the lab. And so then the idea that we had was we could actually use this to make a device where the microwave photons feel like space is curved. And so what we wanted to do was make something that was reminiscent of general relativity and actually have significant curvature in our labs, right? So we know that there's space-time curvature in the universe, but any place where there's enough gravity for there to be significant curvature, there's also gravity to crush things. And so what we can do with this device in the lab is sort of separate these two things out. And so we can put the curvature for the microwave photons without having to move the lab to somewhere where the universe itself is actually curved. And so since I don't want to do any GR, it's got way too many indices. I like to look at a more intuitive and sort of geometric picture of curvature. And so, we're used to flat, so-called Euclidean curvature. And then the other case that we are familiar with is positive or spherical curvature, right? So this is what happens on the surface of a sphere. And so if you try to think about how is the surface of a sphere different from flat space? So one big difference is that in flat space, parallel lines are parallel, right? But if you have two parallel lines on the surface of a sphere, then they will eventually meet. And the other thing is that the surface of a sphere is sort of smaller than flat space. So if you take like a hemisphere and you try to flatten it, you would need to stretch the equatorial region to get it all to go flat again. And if you start drawing polygons on the surface of a sphere, then you find out that they're sort of flatter, they're fatter than your usual counterparts. The other case of curvature, which is the one that we decided to do in the lab, is much harder to picture. The easiest way to do it is actually to go get an MC Escher painting. But you can also think of it as being opposite to spherical curvature. And so the problem with the hyperbolic plane is that you can't have a hyperbolic surface in 3D. It's too big to fit. And so there's no analogous picture. Here's the surface of a ball, that's spherical curvature. There's no surface that you can draw that is uniformly hyperbolic. And so we have to take our intuition from just thinking it should be opposite to spherical in every possible way. And so instead of parallel lines converging, they're actually going to diverge. The surface is exponentially bigger than flat space, and the polygons are skinny. And so this is the general idea. And so what we're going to do is we're going to use these guidelines to basically make a pattern that's periodic in a hyperbolic space, but not periodic in the lab. Okay, let me skip that. Okay, and so this is a picture of a honeycomb tiling, which is a nice periodic structure in 2D Euclidean space. You take these hexagonal cells and you just keep repeating them, et cetera, et cetera. And so now we can try to think of what is the analog of this honeycomb on the surface of a sphere. And the way that one of the ways that you can do this is instead of using hexagons, you try to use a different polygon. And so if you try to use pentagons, you can actually make a honeycomb-like tiling on the surface of a sphere. It's actually the dodecahedron. But if you start trying to draw this on a flat surface, you have the problem. So here I've put together 3 tiles. They share one corner, great. But the problem is that this corner here should be the same lattice site as that corner. And if I use regular polygons to draw this, then this isn't possible. And the only way to fix it is to stretch things out. And so this is my cartoon picture of a flattened half soccer ball, right? So, you know, you can imagine having a lattice on the surface of a sphere that is in the pattern of a soccer ball. This is actually a molecule known as Buckminster fullerene. But if you wanted to flatten it out, you'd have to stretch out all of the bonds, and that would change the physics. And so our goal is to take this curved space model that we're going to have to stretch, but keep the physics the same. And that's what actually having our CPW resonators allows us to do. So this is the spherical case. The hyperbolic case is opposite. Instead of having too much space, you have too little space. And so you have to compress things. And so what you should imagine is that somewhere in an abstract hyperbolic space, this particular tile, exists, and that each one of these heptagons is actually exactly the same size, but you're just looking at this world through a fisheye lens. And so this one is big and the others are far away, and so it looks small. But what we want to do is take this physics where each and every one of these loops is the same size and produce it in the lab, even though what we have to do is actually compress the loops. Okay. And so the trick, of course, is to use the shape of the coplanar waveguide resonators. And so like if we go back and look at the soccer ball example, then here in the middle, the distance is short. And so you put on a resonator with a big meander. And then here on the outside, the distance is long. And so you put on a resonator with a smaller meander. And so what that does is it guarantees that from the point of view of the microwave photon, every single one of these things is the same length. You had to change the shape in the lab to actually achieve that, but the microwave photon doesn't care. It's just going to happily follow its little waveguide. And so in this way, we can take a puddle of a curved space and just smash it flat without actually changing the physics. Oops. And so this is what it actually looks like. So this is the device that we made when I was a postdoc. And so this is our hyperbolic honeycomb lattice. And so the way that you should look at this is that these glowing lines are the coplanar waveguide. And so for example, here in the middle, you have a ring of 7 resonators, 1, 2, 3, 4, 5, 6, 7. And then if you keep going, the next ring also has 7 resonators. It's not round anymore, but from the point of view of the microwave photon, it's 1, 2, 3, 5, 6, 7 hops to go around in a circle. And the smallest loop you can do at any point on this lattice is 7 hops to go in a circle. And so from the point of view of the microwave photons, this is a hyperbolic honeycomb lattice. It's a small piece, but it is actually very strongly negatively curved from the point of view of the microwave photons. And so this was the device that we made when I was a postdoc. Here's the very messy data that says it's basically what we thought it was. But so what I want you guys to take home from this is this idea of the flexibility of these circuits, that you can really choose how you want to implement things. And in particular, that if you have these waveguide-like resonators, you can change the shape and sort of stretch and crunch things without really changing the physics. Unfortunately, when you go into the lab, there are some parasitic effects that you have to smooth over, but you can fix them all. And so we can take basically a model that we've chosen for physics interest and print it into the circuit by really leveraging just how much configurational choice we have in how the circuit is made. And so in this particular device, it consists only of resonators. So it's basically a harmonic oscillator network, but photons moving in this device, they move as if they were in a very, very strongly negative space. And so what my lab is now doing is trying to take this device beyond just coupled harmonic oscillators and start to put qubits inside, because then we can have interacting photons in curved spaces, and we can also start to use the hyperbolic geometry to engineer qubit-qubit interactions. But also there's a much more general idea here, which says that I have a huge amount of freedom in how these resonators are connected together, and I'm not really limited same constraints that I would have with real atoms, right? There are platforms that would, for example, allow me to put an atom at every one of these dots, but these outer dots would be much more strongly coupled than the ones in the middle. And this is what we can avoid with the circuits. And so we really have this playground where we can select our connectivity. Those of you that have had the right math classes, basically this is graph-like. You have a set of vertices and you decide who is connected to whom and how strongly, and the physical distance of the link is relatively meaningless. That's what we have here. And so this hyperbolic lattice is just one particularly dramatic example, but we're really free to choose. And another thing that we can make that turns out to come out naturally from these systems is lattices with flat bands. So you end up with very, very large sets of degenerate states where it's like the kinetic energy vanished, essentially. And this is what we are playing with. And so then I think I will just skip to thanking everyone that was involved in this. So the things that I've shown you is a subset of a pretty big body of work that a very large number of people have been involved in. In particular, my postdoc advisor, Andrew Hauk at Princeton, and our math collaborator, Peter Sarnak, who has really helped us to understand the kinds of systems that are accessible given our flexibility. And then a series of students, in particular, Matthias Fitzpatrick was a graduate student in the Hauk group when I joined. And so I was thinking about what I should be working on. And actually the first grad student that I was supposed to work with in that group essentially refused to speak to me. She wanted to work by herself. She didn't want me in on her project. And then I had this hyperbolic lattice idea, and Matthias and I immediately joined forces. We decided that two heads was better than one on any project. And so we pooled his projects and mine and launched into this together. And without his fab skills, we never would have made that device. It was really a combination of his microwave circuit expertise and a couple of wild and crazy ideas that sort of got very lucky and snowballed that we were able to pull this together. All right. Hopefully that was mildly interesting and mildly comprehensible.
Oh, yeah. Thank you so much, Professor Kollár. And please ask question freely if you want. Oh, while others are thinking about question, I have one question about the, like, as you said, even though we project the curved thing into the flat thing, the physics is not changing. So I just wonder whether like everything is same in these cases, or is there some limitation when you like project the thing in the flat space?
So the way that I like to think about this is, if you're using a computer and you want to simulate some set of equations, right? Then the first thing that you will probably do is discretize the problem, or set up a mesh, basically. And so the idea sort of here is that imagine in some abstract space you have a continuous problem, and then you mesh it. And then the key is that you have a new discrete problem on that mesh, which you can realize in a completely different way. And so that's really what's going on here, is you take a discrete version of the problem and you say, okay, it came from a continuous problem that I was interested in, and I can't bring the continuous problem into my lab. But the discrete problem is actually much less constrained. I just need the connections to be right, and then I can have the discrete problem. And so you can take the meshed version to the lab, even though I can't actually make a hyperbolic surface in my lab. I can make a hyperbolic graph. I can make hyperbolic connectivity. And that's really how I think about this, is that I start from some imaginary space, I make a discrete version, and then I pull the discrete problem down into the lab. And to the extent that the mesh is fine enough, it tells me about the original problem, or it tells me about a lattice problem in the original space.
I see. So it's kind of the simulation of the real hyperbolic or kind of curved space into the kind of flat space, so that we can know the curved space better and the properties.
Yeah.
I see.
And, I think one of the really key insights is that once you have discretized a problem, then you have a finite number of points and you have a finite number of connections. And at that point, it doesn't matter how you get those points to come into existence in your computer, or how you get the connections to come into existence in your computer. As long as you can get that set of points and that set of connections, you have the original problem.
I see. Oh, yeah, thank you so much. And any other question?
I'll ask one if no one else. Oh, Pedro, please go ahead.
I just have a quick question. What are you trying to leverage with the design? Like, if you put qubits into the design, what are you trying to communicate them in a specific pattern to allow some specific communication? What are you trying to leverage there?
Well, so basically, one of the strengths of superconducting qubits is how large the light matter interaction is. And so that means that if you put two superconducting qubits into one of these resonators, then via the photons, they talk to each other very strongly. But the physics that you get from that is very simple. It doesn't have any interesting spatial structure. And so when you put a qubit into one of these photonic materials, then one of the things that you actually produce is you give the qubit a long-ranged interaction profile. And this has been done before in simple 1D chains. And in this case, what you give it is an exponential tail, which is better than a delta function, but in some sense, it's too fast. This is short-ranged. And so one of the things that we're trying to do is to give it a more interesting profile, something with longer tails, such as power law, or hyperbolic. Actually is this very, if you think about it from a connectivity point of view, hyperbolic space is very weird, because what you end up with is systems that are very highly interconnected for the number of sites that you have. And so if you have competing terms or competing interactions, you expect to get more interesting things in that geometry. But it's really to sort of get away from this, I talk to my neighbor and I'm done, very, very simple interaction that is native in a single cavity.
So would you be able to apply that for example, baths and stuff, and be able to control one qubit better in some way?
Yeah, so I think the more natural thing is to try to make an interacting spin model. You also end up with actually a very large amount of control about where a qubit decays to. Like when it gives off its information, where does it go to? These are actually just two sides of the same coin, this photon mediated qubit interaction and sort of controlling the emission. It's kind of a matter of perspective, which one of these things you think it is.
Great, thank you.
Oh, Whitman, did you have a question?
Yeah. Perhaps if no one else has a question, I'll just ask a quick one. I was like thinking about the graph you showed for the heptagonal setup, and I was like wondering if the data they're showing that theory predicts the situation well. Like, does it give like any insight like how physics might work, hyperbolic geometry or something like that?
The truly frank answer is no, because if what I wanted to do was study the single particle physics on the hyperbolic graph, my laptop can do much bigger sizes than we can actually do in the lab. And so this is a stepping stone to a nonlinear device, something with quantum mechanics and with interactions. We have actually learned things by trying to understand this device, but it's been a little bit of a backwards thing. So one of the things that I didn't actually have time to mention is that that particular hyperbolic lattice has a very unusual feature. It has a flat band that's all by itself. So about 20% of the eigenvalues are -2. And then there's a range where there are no eigenvalues, no eigenenergies, and then everything starts. And this is very, very strange in materials physics. And the first time we saw it, we thought this was some crazy hyperbolic property. It turns out that what it really comes from is having these odd-sided loops, and we have since been able to figure out Euclidean lattices that have this property as well. And so in a sort of amusingly backwards route, we made a crazy curved space general relativity device, and we accidentally learned something about crystallography in normal spaces, trying to understand what was going on. And actually, the Princeton folks are in the process of searching materials databases to find actual materials that have lattices of this kind, with the property that we first saw in this hyperbolic example.
Yeah, that's really interesting. Thank you so much for sharing.
Yeah, and any more question?
I mean, just elaborating on that a little, I don't know fully what eigenvalues of -2 must mean. It just sounds like really strong attenuation to me. And I was just wondering if maybe you could give us a little insight, just a hint what that might mean.
Yeah, so kind of, I think the right way to think about it is that sort of almost everything that I told you so far was single particle physics. And in many cases, when you add interactions, the physics doesn't change qualitatively. It can be a lot harder to compute what goes on, but it's sort of is mostly the same. And so there's a general kind of rule of thumb, which is that the most interesting physics and the most hard to understand physics usually comes when the interacting physics is totally different from the non-interacting physics. That the single particle physics gives you almost no intuition for what's actually going on. Famous examples of this are, superconductivity way back when, the fractional quantum Hall effect and things like this. And sort of with that idea in mind, you can ask the question, when would it be that the interacting physics is very different from the non-interacting picture? And so what it turns out is that the interactions are usually competing with kinetic energy. That if you want to do something exotic, then this will often have a very high kinetic energy cost, and so it won't actually happen. And so having a very large set of degenerate eigenvalues in the non-interacting problem means that when you add an interaction, it's free to pick and choose any combination of those states that it wants without fighting with a boring term like kinetic energy. And so that's really sort of the intriguing thing, is that interactions would have free reign to do whatever they want in this region of the eigenstates. And so in this case, it happens to be at a certain energy of -2 hopping units, but it's really the fact that there's this huge number of single particle states that are all at the same energy.
It gives me a lot to look up. Thank you so much.
I'm not sure that means it was a good answer or not, but.
Oh, it definitely does. It was an amazing answer. Thank you.
So, all right. Yeah, so it looks like we are nearing the end of our time. So Professor Kollár, as is tradition, we would like to ask the first speaker for a quick word of advice for young physicists looking to start their journey through physics. So please.
I think maybe my main word of advice is that there's no one good path, right? I think a lot of people worry that if I do this now, then it will sort of determine all of my choices going forward. If I don't take solid state now, then I'll never become something. And my experience in physics really has been that every time I dug into a different place, I found interesting things that I had no idea were going to be there. I started my first summer undergraduate job and I had no idea I was, going to learn how to build support structures for a building. And so I think one of the things that means is that, work on stuff that's interesting, work on stuff that you find cool, work with people that you like working with, and don't worry too much about, is this the right choice and will it lead me to the best next step or the next step? Like sort of there are many different interesting ways through physics, and you can wind up in a field you never planned to be in. For example, the field where I did my PhD work of ultra-cold atoms, there was basically no one at my undergraduate institution that did that. And so I didn't even know it was a thing, and I loved it. And so this sort of, don't plan too much, something like that. I think that's my advice.
Thank you so much, Professor Kollár. And yeah, it was really a pleasure to hear about your career and your current research interests. So for the next few weeks of Quantum Summer, we also have a lot of exciting lineup of speakers. So please attend as well. And I hope to see you all next week. And again, thank you so much, Professor Kollár.
All right. It was very nice talking to you all. All right. Have a nice
Thank you so
evening.
much.